The next talk today will be by Dr. Pete Mosley, Senior Lecturer at the University of Bath. And the talk is entitled Photonic Crystal Fiber for Quantum Technologies, Sources, Networks, Interfaces. Go ahead.
Great, thank you very much. Let me just find my slides. Okay, thank you very much. Thanks for tuning in, everybody, and thanks a lot to the organisers. It's a real pleasure to be here at BQIT. I first spoke at BQIT 2014, which seems like a really long time ago now, but it's great to be back. So some of the stuff that I'm going to talk about today will sort of close the loop a bit maybe on what I was talking about back in 2014. So I'm going to be talking about work we've done over in Bath, applying photonic crystal fiber to various things within quantum technologies. And specifically, I'll talk about the work that we've been doing on all-fibre multiplexed single-photon sources. So that'll be hopefully relatively brief. And then I'll move on to talk about what we've been doing around frequency conversion of photons for quantum networks. And so everything that I'm going to talk about today involves photonic crystal fiber, so microstructured fiber. And there are some images of some various different types of photonic crystal fiber shown on the slide here. So up in the top right-hand corner, we've got a fairly conventional PCF with a silica matrix surrounded with these small air holes, which are the circular inclusions that you can see, and a core in the middle where a missing air hole forms the refractive index contrast to enable light to propagate down the fiber. And actually pretty much everything I'm going to talk about today just involves this relatively standard type of photonic crystal fiber that we fabricate over in our facility here in Bath. So first of all, a bit about the single photon sources. So we've just had a great introduction to single photon sources, so I don't really need to say anything about what we want. So we want identical single photons delivered simultaneously by independent sources. And we want to be able to take a bunch of those sources and feed single photons into a network of logic gates with some detectors at the end. And within those logic gates, we need the photons to interfere with one another. And so therefore we need them to be indistinguishable from one another. And as we've just been hearing from Don, one of the ways in which we can do this is by spontaneous four-wave mixing. And here we have a pump laser pulse, which propagates through a nonlinear material to generate photon pairs that are the signal and the idler. And then we can detect one of those photons to herald the other. And the particular schemes that we use in Bath involve pumping at 1064 nanometers, so a nice convenient laser wavelength, and generating signal and idler photons at 800 nanometers and at 1550 nanometers. So it's nice to have a signal photon at 800 because then we can use silicon detectors, which are room temperature, robust, efficient, and at least relatively speaking, reasonably cheap. And producing our heralded photon at 1550 nanometers gives us access to low loss components from telecoms technologies. And typically, because of the energy conservation between the two pump photons that we annihilate and the signal and idler photons that we create, the signal and idler pair end up being anti-correlated in frequency. But photonic crystal fiber is really nice because by controlling the structure of the fiber, so that means deciding on the separation of the air holes and the size of the air holes, we can control the group velocity dispersion within the fiber. And by playing this little trick where we engineer the group velocity of the pump to be in between the group velocity of the signal and the idler, enables us to eliminate that spectral anti-correlation between the signal and the idler photons. So in this case, we've generated our signal photon around 800 and our idler photon around 1550, but we've done so in this joint state that's quite close to a nice circular blob, so it doesn't have a lot of spectral correlation in it. And that gives us very little distinguishing information. When we detect a signal photon to herald the idler, we don't learn much about the idler photon, and so it can remain in a pure quantum state when it's heralded. So by designing our PCF carefully, we can build this PCF into an all-fibre heralded single photon source. So we have our pump laser, which couples into the piece of PCF where we generate our photon pairs. Then we have fibre Bragg grating to reject the pump, a coarse wavelength division multiplexer to split things up, that's also in fibre, so that we have our signal photon delivered in this channel at the top, and our idler photon delivered in the channel at the bottom, with some additional fibres that I'm not going to talk about today to give us more isolation from the pump and noise rejection. So that's great, and we can generate these nice heralded single photons at 1550 in approximately pure quantum states. So far, so good. So back at BQIT 2014, I made this slide, which is a rather dangerous slide to show, particularly when you're at a virtual conference where you can't even see who's in the audience. But the point that I was trying to get across with this slide in 2014 is that the generation rate or at least the generation probability with these sources based on four-wave mixing is typically rather limited to something like 1%. And that's done to limit the impact of the higher order photon pair contributions to the joint state. And so because we're only generating photon pairs on about 1% of our pump pulses, then if we have a lot of independent sources next to one another and we want them all to fire at the same time to produce 1, 2, 3, 4, here up to 12 separate heralded single photons from independent sources, then we have to wait a long time for all of those to work simultaneously. And of course, this is a big problem. And if you look at the scale of the plot on the left-hand side, then for the fairly arbitrary numbers I've picked here, we end up waiting longer than the age of the universe for 12 photons. So, of course, this is not a great situation, but there's been a huge amount of work that's been done since 2014 to use source multiplexing, so these ideas around active switching and feed forward to solve this problem using these spontaneous sources. So how does multiplexing work? Well, rather than just having one photon pair source, we have several next to each other, and we pump all of them simultaneously, and each one has a heralding detector. When that heralding detector fires, it feeds forward to a switch network, which enables us to set the state of, in this case, 2x2 switches, so that if one source fires, here the second one down, then the heralding detector sets the state of this switch network to route the remaining heralded single photon through to some master output. And by combining the probability of generating these heralded single photons across lots of different sources or lots of different modes, we can really increase the probability with which we can deliver these heralded single photons. And again, by picking some fairly arbitrary numbers, we can really reduce the waiting time for relatively large numbers of heralded single photons. And of course, the better we make all of the components involved here, the shorter the waiting time becomes. And we can modify the photon statistics effectively in this process to get back from what was a completely ruinous situation where we had to wait forever to get a large number of independent photons to something that's much more manageable. And this is something that we have implemented over in Bath. So back when I spoke in 2014, we got a bit of money to do this, but hadn't really got there yet. But we built two of these heralded single photon sources next to one another with a couple of detectors at the end and a 2x2 switch, some homemade FPGA electronics to enable us to feed forward to that switch and to increase, in this case, the coincidence to accidental ratio by multiplexing over these two sources to get better performance than we could with each source individually. Of course, if you want to do this over lots of sources to really increase the probability of delivering heralded single photons, then it rapidly becomes very intensive in terms of the resources that you need to implement it. So a second experiment that we did back in 2017 was to do a similar thing in the time domain where we had a switchable delay loop. Again, this whole thing is in fibre, all spliced up without any alignment beyond coupling into the PCF at the beginning, and storing photons in this delay loop for multiples of the laser repetition rate and switching them out on some particular clock cycle, again, to enable us to increase this coincidence to accidental ratio by multiplexing in the time domain, where the overheads in terms of the resources that you need are not quite so intensive. So that's some of the progress that we've made on that front since I last spoke at BQIT, which was quite a long time ago now. The other thing that I wanted to give a little update on is the work we've been doing on frequency conversion of single photons to build quantum networks. And this is something that's really come out of the membership that we've had of what was previously NQIT, the Network Quantum Information Technologies Hub, that's now metamorphosed into the second phase, QCS, the Quantum Computing and Simulation Hub. So the goal of NQIT, which was slightly different perhaps in some respects to QCS, as I'll explain in a minute. The goal of NQIT was to build components for quantum networks, and those quantum networks were of two different types. One was local networks for information processing, and the other was long-distance networks for communications. And the architecture of those networks was that the nodes would be trapped ions, here shown in this nice picture from David Nadlinger in Oxford, in David Lucas's group. So the nodes are trapped ions, and those ions need to talk to each other with photons. So if you want to build a local network for information processing, you need more than one node, because you can get maybe 10 or 20 trapped ions in one trap, but you need more than that to do useful information processing tasks. So you need to build several nodes and have them talk to each other. And of course, if you want to do long distance communications, then you need your nodes to be able to talk to one another using photons, ideally transmitted down optical fiber. And so within the NQIT network architecture, the trapped ions that we used were calcium ions for the information processing, and then strontium ions to talk to the outside world in this dual species trap. So strontium ions are great from the point of view of ion trappers, but not so good from the point of view of people who do photonics. So the ion trappers have a favorite transition that they use within strontium to get photons in and out, and that's this 422 nanometer transition. But there's also an alternative transition at 1092 that could be accessible if the strontium ion were contained within a cavity. So these were the two wavelengths which were really available to us in the NQIT hub. But if you look at either of those wavelengths, then the attenuation that you get when you send them down conventional telecommunications fiber is very large, and this plot only goes down to 800 nanometers wavelength. So at 400, the attenuation is huge, but even at 1 micron, it's still relatively high. So our job was to link 422 nanometers and 1550, so the telecommunications band where the fiber loss is very low, and also to link this alternative transition 1092 with the telecommunications band at 1550. So the 422 work I'm not going to talk about today, because that was done by sum and difference frequency generation, so not in optical fiber. Today I'm just going to update you on the progress that we've made at linking 1092 and 1550 in a frequency conversion interface. So this frequency shift between 1550 and 1092 really makes it too small for practical sum and difference frequency generation. Instead of that, we can use a four-way mixing process, in our case in optical fiber, and that's the Bragg-scattering four-way mixing process. So here we have two pump fields labeled P and Q, and we can shift a source photon to a target wavelength by a frequency shift that matches the difference between the two pumps. So typically, we need two separate pump lasers to drive this process. And the first experiment that was done on this front was back in Mike Raymer's group in 2010. And they used two locked titanium sapphire oscillators as the pumps. So one at 808 and one at 845, and shifted a signal photon at 683 to a wavelength of 659. And so the question that we had looking at this implementation was, can we use the nonlinearity in PCF to reduce the physical resource requirements here? So rather than having these two pump lasers, can we reduce it to just using one pump laser? And the way that we approached this was to design a PCF in which we could use a single pump laser to generate a second pump wavelength, so we could generate synchronized pump pulses with a wavelength separation that was the same as the frequency shift that we wanted to impose on our source photon. So here's a PCF that we used for a seeded four-way mixing process, pumped at 777 nanometers by a TISAF laser and seeded at 977. So we have amplification of this seed and generation of a conjugate four-way mixing wavelength in this first piece of PCF, and the separation between the pump and the seed is the same as the frequency separation that we want, the frequency shift that we want for our source photon. So then we take these two pump wavelengths, which will be 777 and 977, and feed them into a second PCF where we do the Bragg-scattering four-way mixing conversion and convert our source photon into a target. And this is something that we implemented. So here are the output spectra just for conversion of weak coherent light. So this is in blue with the source at 1550 off, and here in red with the source at 1550 on. So we've got our original 777 pump over here, a 977 seeded four-way mixing. So these are the two pumps that drive the Bragg-scattering four-way mixing process. And then when we have the source wavelength input, we generate some output at 1092, which is our target wavelength. In this frequency conversion process, we managed to get efficiencies just in excess of 50%, which is pretty good, over a narrow bandwidth here around 1530 nanometers. And we did the reverse process, going from 1092 to 1550 in the same piece of fiber. And hopefully you'll see this published soon in a high quality journal near you. So with the conversion efficiencies that we managed to achieve, which was 50% in one direction and only about 3% in the other. Nevertheless, if you're thinking about transmitting these photons over more than about 10 kilometers in fiber, you still end up doing much better in terms of your transmission probability by implementing these frequency conversion techniques than the loss you get by direct transmission at 1092. So that's where we are at the moment. What are we working on now? Well, typically the phase matching of these frequency conversion processes is limited to one set of wavelengths. So here at the bottom left is the phase matching diagram for a process to convert here a wavelength of 1092 to 1550. And the dotted red line here represents energy conservation, and the yellow areas are the momentum phase matching. And you can see, oh, sorry, I need to go back. And you can see that they intersect just at one set of wavelengths. So for conversion to 1550. However, if we design our PCF very carefully, we can get those two conditions, the energy and the momentum conservation, to overlap over a wide range of wavelengths. And that gives us, or could potentially give us, high conversion efficiency over a wide range of source wavelengths, all to 1550. And it turns out that the way in which we can engineer that process is by imposing group velocity symmetry within our PCF. So I don't have time to go into the details of that now, but there will be, in about 10 days' time, a talk at Virtual Clio by one of my students, Charlotte Parry, and Charlotte will give a lot more details about the ultra-tunable frequency conversion processes that we can engineer in these PCF structures, and that's something that we're working on at the moment. Okay, I've been given my hurry up by Jorge, so I will summarize. I told you a little bit about the progress that we've made since my last BQIT talk back in 2014 on multiplex single photon sources, and we're doing more work now developing new fibers for that. And my thanks go to the people involved in that who are listed here, and also everyone who's been involved in this frequency conversion for quantum networks, so linking the wavelengths that are of interest for NQIT and now the QCS hub, and Charlotte going on to work on this ultra broad frequency conversion process. And thank you very much for your attention.
Thank you very much. Again, we have quite a few questions. I'm going to start by asking one myself, if possible. So in terms of the multiplexing source, how does the dispersion and absorption of your fibers affect the timing that you can apply to your switches and your FPGA process? I know this is quite an issue in integrated photonics, so I wonder how, in terms of fiber, it is affected.
Yeah, that's a good question. So, excuse me, for the sort of fiber lengths that we're using in our sources, we're only thinking, well, we're only using maybe 25 or 30 centimeters of PCF. So the absorption in that length is very small. So the intrinsic loss of the fiber is very low. And because we're generating at 1550, we need about 100 meters or so of SMF28 to give us the required delay to feed forward to the switches. So also in there, the loss is relatively low. Really, the dominant losses that we have are from interfacing different fibers with one another. And I didn't have time to talk about it today, but we have also, as in Dom's talk, we have these adiabatic mode converters to get between the different fiber types. And so we put a lot of effort into really engineering the loss of the whole system down. And we've got to the point where the loss through the whole thing, from the beginning of the PCF to where we get to the detectors in each of those channels, is about 5 dB.
Thank you. Now, one question from the audience from Zixing Huang. How do you think the overperformance multiplexed SPDC compares with other supposedly deterministic sources, for instance, quantum dots?
Yeah, I think that's a really good question, and I think I don't have an answer in terms of you know, who's going to be the winners, all the rest of it. Well, science is the winner, right? Something that I'm really looking forward to, though, is within the QCS hub. One of the new partners that's come on board is Anthony Bennett in Cardiff. And so we're going to be doing some work within the QCS hub with some quantum dots in microcavities from Anthony Bennett, and trying to interface those with some of our PCF as well. Yeah, that's a complete non-answer to your question, for which I apologize. But something that I'm really looking forward to is learning a bit more about the quantum dot sources and looking at the interfacing between quantum dots and fibers, and then looking at how we can compare that performance with the spontaneous four-way mixing.
Thank you. And another question from the audience from Francesco Graffiti. What symmetric and then antisymmetric or asymmetric measured heralding efficiency do you achieve with your PCF source, and what is your detector's efficiency? Okay, so the detector efficiency I can answer easily. So for the silicon detectors, it's about 70% at our wavelength, and for our in-gas detectors, we were running them at about 20% detector efficiency. The heralded detection, so the heralding efficiency, I actually can't remember the numbers off the top of my head. I hope it's in the paper that we wrote, but that was a couple of years ago now. If it's not in there, drop me an email and I will dig it out of Jamie Francis Jones's thesis, because it's definitely in there. But I'm sorry, I can't remember that number for you off the top of my head. That's right. Thank you very much. And in interest of time, let's move on. And again, questions will be transferred to the corresponding Slack channel. Please contact Pete there. Okay, thank you, Pete, again.